At the end of the last lecture on line search, we had an introduction of what we will seek in inexact line search. So basically, there are several um, competing rules for inexact line search. That is, there are several competing uh, checks by which you can um, um, prematurely terminate a line search process. In this lecture, I will outline two of those. One is Wolff's conditions, and the other is Armijau's rule with tracking. As it happens, Armijau's rule is a part of Wolff's condition also. Okay. So the basic idea of inexact line search is to relax the minimality condition for fx along the ray on which we are conducting the line search. And we will do this for efficiency because we recognize that the resulting solution is not final. From there, a new direction and therefore a new search will be initiated. And we also know that in the last steps of the line search, the progress is actually extremely slow because by that time, the direction, the line of the line search gets too aligned with the shape of the contour and the improvement is very little. So we are going to develop rules by which we will terminate the line search prematurely. So here we have two conflicting notions at play. One is try the direction enough, but not too much. That is not when it is no more worth. Okay, when there is no advantage. In other words, the function during the line search, the function should sufficiently decrease before we quit the chosen direction. But after that, we should not keep on wasting more and more iterations for pittance of an improvement. Okay, so these two conflicting things have to be balanced. Now, during line search we keep on getting alpha values in a sequence, and the way a univariate optimization method works, it does not go on monotonically increasing or monotonically decreasing the alpha values. The way we think is that from xk we choose a direction and then proceed along that. So our thought process may be as if we are marching along that road, but the single variable optimization algorithms don't operate like that. They bracket, and then in that bracket they try to squeeze, sometimes producing a point further away, sometimes producing too close compared to the minimum point, and like that. So it is not that you will cross the minimum and you will notice if you follow one of these methods like bisection or golden section search or whatever. Even Newton's method may go back and forth. Okay. So we will never get the notice of having crossed a minimum. So it is important to have rules independent of crossing anything to quit whenever we find an alpha that is good enough and after which not much more progress is likely to happen. So these two things we have to capture. So first condition in any such inexact line search conditions will be Armijau's rule because that is something very basic. So that is a basic check for acceptance of an iterate. And alpha is okay if it satisfies this condition. Now we need to understand this condition. Say this is alpha, this is psi of alpha. Okay, and at alpha equal to 0, it starts from the value f of xk. And suppose this curve is the function psi of alpha. Now at this point, this is the tangent, and the tangent line I am denoting with as L1, and that is at alpha equal to 0, the value is fxk, so that is here, and the slope is this dk transpose grad fxk. Okay, with that slope it decreases, so that is why that slope is here. Make note that this will be negative. Okay, so this whole thing, the directional derivative, you can call as psi prime 0, psi prime at 0, that is the slope at this point. So that is this tangent line. Okay, now we know that at this point, whatever rate the function is decreasing, that high rate of decrease will not continue. It will become a little shallow like this, and then there will be a minimum which we are actually looking for, after which it will rise. That is a typical expectation. So we expect the curve of the function psi to be above the tangent. Okay, how above? So put a quantitative measure for that. Say mu times. Mu is less than 1. Okay, so if you, so this is steep line, make it a little gentler. Okay, so whatever is this slope, if you multiply that with mu, that is this mu. Okay, mu is less than 1. Okay, then you will get a gentler line. Okay, so it is something like telling that, well, at this rate it will not decrease, but I'm ready to go this far if compared to this rate of decrease, at least 10% it decreases. So that 10%, that notion is somewhere here. Okay, so as a mu, if you put a mu which is less than 1, then rather than this line, you will get this line, that is L2. So in place of psi prime here, if you put mu times psi prime, then with that gentler slope, this line, this cut line is L2. And Armitage's rule simply says that for acceptance of an alpha value to be okay, is that at that alpha value, wherever is the function, that point is below this line. If it is above, somewhere here, then you will not accept it. What is this? You go so far and yet so little decrease of the function value. We will not accept it. Okay. So below this line, you want, that is Armitage's rule. Okay. So accepts a value below AB. This point is A, this point is B. Okay. Again, wherever it cuts next. Now, the problem is that it accepts any point on the curve below this line, even a very small value. And that means terminating a line search will become so easy. That is, you take 0.0001 and you get a point which is just a little lower, but that is certainly lower than this, lower compared to this line, so that will get accepted. So a point gets accepted very easily. Okay, so that means the direction does not get utilized up to the hilt. More hope was there when it was left, and that is why only Armitage's rule is not enough. So we're telling that for this much journey, enough decrease has taken place, agreed. But if we journey a little more, the hope is not yet exhausted that it will improve further and further. So we look for another condition which says that after this, not much is going to happen. Okay, so that condition we want. So for that, we have a curvature condition which says that, well, at this point, it is decreasing with this rate psi prime. And we will keep on hoping that it will decrease further, if that good rate, if not completely, but at least eta times of it continues. Now, what is eta? So, another fraction less than 1. Okay. So, here it is decreasing at such and such rate. We will go on trying more if at least 20% of that rate goes on continuing. That means that eta is 20%, 0.2. Okay. So, as long as that continues, we will keep on trying. When the rate of decrease turns out to be less than 20% of the original, of the initial, then we say, no, this is, no, not much hope further. Let us stop it here. And whatever we are talking about, that below that we will quit. Here in the condition, it says above that we will quit, because we are talking about, verbally we are talking about the magnitude, rate of decrease we are talking about. Now, both of these numbers, these rates are negative actually. And that is why this side higher means actually when its magnitude goes lower than 20% of the original magnitude. Okay. So while studying this, while reading this, be careful that on both sides we have negative numbers. Okay. So eta is also less than 1. It's a proper fraction. So these two rules, Armitage's rule and curvature condition, together are called Wolff's conditions, which is a complete set of conditions for inexact line search. And now notice that if you put this condition, then whatever is the slope here, eta times that will be the slope somewhere along this red direction. Okay. And parallel to that is a tangent here at C. So that means curvature condition will accept a point only beyond C. From A to C, points from A to C will be rejected, because from here to here, the rate of decrease still remains something. Okay, so we still keep on hoping. Beyond C, as you continue, then the rate of decrease becomes so low that negative that will become lower than this, and it will be accepted. Negative that will become higher than this. Okay, so that will be accepted. So beyond C, the points will be accepted. From A to C, so little improvement, it will not accept. So it wants more. That is, it retains hope, so it continues. Okay. Now, these two things together are called Wolff's conditions. However, make note that psi prime 0 is negative. We know that. This one is on this side negative. On that side, it is positive actually, beyond the minimum. Okay. And this actually brings a little asymmetry in the curvature condition. On the other side of the minimum point, any point will be accepted by it immediately. Okay, even if it is very high. The reason is that on this side it is negative, and on this side whatever positive comes, it will be accepted. Okay, so a large positive value also will be accepted. But that means that beyond minimum it is far away. Okay, so we will correct it soon. I mean, but this is also fine. These two things together, what is Wolff's condition, this is actually used by many people. And the hope is that on the other side, Armitage's rule hopefully does not allow too much, but sometimes it does. If you take mu to be very small, then Armitage's rule will allow a point much beyond the minimum point also, which is actually not a good point. Okay. So now, what are the values of mu and eta? The typical values. Mu should be quite small to safely enclose the minimum point for diverse possible profiles. What is psi? What is the profile of psi of alpha? We don't know. So irrespective of whatever may be the profile of psi of alpha, mu should be small enough to have a large domain, certainly including the zone of the minimum point itself. Okay, eta has to be considerable to allow a band around the minimum. If eta is not sufficiently large, okay, if it is very small, then it allows only a very narrow band near the minimum point, and that means too many iterations would be required to reach there. Nocedal and Wright suggest mu to be something like this. In my understanding, this is too small, and I think these authors have suggested it to include all sorts of very crazy function profiles also. But it also would be like this: 0.1, 0.2, some reasonable fraction. However, now we address the asymmetry condition also. That on the other side, beyond the minimum, it should not accept too far away points. So for that, all that we can say is that, okay, this is negative and this is also negative, and you wanted the condition to be that this side is higher. So actually you mean that the magnitude of this should be lower than the magnitude of this for termination. Okay. So just say that we want the comparison between magnitudes. So put the comparison between magnitudes, and of course the inequality sign will reverse. Okay, because this was negative. This was actually unnatural kind of condition. This is natural condition. Okay. So just say this, and this is called Strongholds condition. And what this will do, yes. So whatever is the tangent at C here, you see, which said that from A to C, these points will not be accepted. With the same magnitude of slope, if you draw another tangent, then this point of tangency D, so beyond D, from D to B, will be again not accepted. That is, further improvement will be looked for, further iterations will be made. So this would allow from C to D. Okay? That is a band around the minimum point. Okay. So this is Strongholds condition. Now let us take one example to operate with this condition. So this is the function, and starting point is 1, 1. Starting direction is -1, -1. You can verify that at this point in this direction the function does decrease. Okay, and we look for alpha 0 to minimize this. It's a line search. And I have used bisection for this little simulation. So before iterations start, this is bracketing 0, 1, 2. The values of the function 33, 13, 17. So that locates a bracket. And at this point also, we can evaluate Armijaux's rule and curvature condition. And as it happens, here Armijaux's rule, yeah, at 0 there is no point in testing anything because from there we are starting. So at alpha equal to 1, Armijaux's rule has been tested and found to pass. Basically, right hand side minus left hand side. This is what we have done. Okay. And here we have tested Strongholds condition. Here also right hand side minus left hand side. So that should be positive for passing. Okay. So Armiture's rule has passed at all points. Okay. Now at alpha equal to 2, actually there was no need of testing because alpha equal to 2 is anyway not a good point. Before that, we already knew that alpha equal to 1 has been found, which is better. So at alpha equal to 2, we need not have tested actually. But anyway, curvature condition fails because it is negative. Again, in the first iteration of bisection, 0 to 1, midpoint is half, 1 to 2, midpoint is 1.5. So at these 2 points, the function is evaluated and found like this. Again, at 0.5, where the function value is 17.938, worse than some function value already found, there was actually no need to test. Anyway, but as it happens, Armiture's rule passes still, curvature condition fails. Okay. At 1.5, this is the function value, this is the derivative value, and both pass. And right at that point, we exit, just after one iteration. Okay. So this is how the Wilks condition determines a point as good enough for a line search iteration. Now with this alpha 0, 1.5, now the outside step in the main algorithm would be like this. And then from there, you can continue. You can actually make another step with the same rules. Now some questions that are actually raised on Wilks conditions. Now these questions I'm bringing from my old classrooms where these questions actually were raised. I told you that Nocedal and Wright suggested 10 to the power minus 4. I normally don't use so low, okay, but it may be important for general very troublesome kind of functions which change very slowly. So that is the first question that we take up. Why is mu so small? The curvature condition, if used at all, takes responsibility of exhausting the potential of the current direction. So Armiture's rule's job then gets limited to ensuring that there is some reduction in the function value. Okay? So that is the prime thing. So even a very small mu value would do. Actually, mu equal to 0 would mean that any reduction would be accepted. Okay, so mu equal to something like 0.01 will mean that very little reduction will not be accepted. Below that, it will be accepted. Okay. So Armiture's rule now here becomes mostly as a safety check to ensure some reduction. Okay. And if you keep a mu very small, that will include a large domain for alpha. Okay. And unless you include a large domain for alpha, you might end up missing the minimum point itself. For example, take this situation where I am using mu equal to 0.5. If I use mu equal to 0.5 or even 0.1, then something bad may happen. You see, here I have used mu equal to 0.5. So here I have profile of a function which is slowly moving. And compared to the rate at which it was changing here, the slope was at 45 degree. Okay. So initial theta, this angle is theta, this angle from horizontal is theta. Okay, is 45 degree for the tangent. Now mu equal to 0.5 will give you a slope for this Armiture's rule cutoff line. Okay, how you will find that? Tan theta is the slope psi prime. Mu tan theta would be the slope of this. Okay, so half tan theta. The tan inverse of that will give you this angle, and in this case, tan inverse half turns out to be 26 degree. So the Armiture's rule cutoff line will be at 26 degree. That means a point will be accepted only if it is below this 26-degree line, and that after A it cuts at C. Okay, and the minimum point of the function happens to be somewhere here at L. Okay, alpha star psi m. Okay, so this zone itself, the minimum point zone itself, will be missed because Armstrong's rule with 0.5 will insist that the point must be below this line, this red line. Okay, so that way, for a slowly changing function, a not too small mu may miss the neighborhood of the minimum point itself, and that would be very unfortunate. That is why mu must be small, certainly below zero point 0.1. Okay, so this is, I mean, much below zero point 0.1. I typically use 0.001 or 0.005, something like that. Another point is, you saw we had 0 less than mu less than eta less than 1. Why should be mu less compared to eta? Why not eta less? Okay. Another question is there a guarantee that a point, an alpha value, will be found to satisfy Bose condition at all? I mean, is there any fear? From the other side, ask this question: is there any danger, any fear that we have set up the situation in such a manner that no point satisfies Bose conditions? Okay, I mean that would be then counterproductive, right? So to answer these two, first of all, consider that we expect a profile of the function in which the function will decrease but at a lesser rate, and then after hitting the minimum it will go up again. Okay, so one thing is that this line, the Armstrong's rule cutoff line, will certainly cut the function profile somewhere. Okay, so the first cut, call it alpha 1. Okay, so at that point the function value is this, right? So that is the point where Armstrong's cutoff line cuts the curve. Okay, now this is AC. Mean value theorem tells you that if AC is a chord and the function is differentiable everywhere in between, then there is a tangent which is parallel to AC, right? So mathematically you say that from mean value theorem you must get an alpha 2 between 0 and alpha 1 where the rate is the average rate between 0 and alpha 1. Okay, so psi alpha 1 minus psi 0 is this rate into alpha 1. Such an alpha 2 does exist. Okay, and now this rate psi prime at alpha 2 then turns out to be this psi prime 0 into mu. Okay, and now note that for mu less than eta, this rate will be greater than eta times psi prime, because psi prime is negative actually. Okay, so since we are taking eta as greater, that is why the magnitude of this side turns out to be greater than the magnitude of this side. Okay, and therefore the condition, as Bose condition says, that will hold for eta larger than mu. Okay. Now this alpha 2 and its neighborhood would satisfy Bose condition, and that is what we saw actually. If you see in the other one, yeah, so this is the alpha 1 point, and a line parallel to this, tangent parallel to this, that point, that alpha 2 and nearby other points would satisfy. Okay, so that is the So we have got the answer to both. That is, we need this in order to ensure this. And from mean value theorem, we know that this alpha 2 and its neighborhood points will satisfy Wolf's conditions. So Wolf's conditions are always satisfied. I mean, there are always points which satisfy Wolf's conditions, that you will not run out of points. And this will satisfy the strong version also. In fact, the strong version gets directly satisfied. That is why the ordinary version gets satisfied with the inequality turned. Okay. Now we raise questions with anything. So we raise an issue with curvature condition. It needs a derivative, and that we don't like if we could avoid it. And it is particularly embarrassing when the single variable optimization method itself does not use derivative. For example, we were using bisection, right? At that time, in that simulation study, we were evaluating derivatives only to check curvature condition. And this is very sad that to solve the problem, we don't need the derivative, but to know whether the problem has been solved sufficiently, we need to check that derivative. This is not nice. Okay, it is actually a wastage of computational resource. So, can we avoid it? And as it happens, there is a beautiful way of avoiding it. A simple and practical way of inexact line search is with Armitage's rule alone. At that time, we said Armitage's rule alone was not sufficient because it would accept anything. And that is something which we have to stop. Accepting anything, we have to stop. Otherwise, Armitage's rule was fine. Now, if we try to address that point, then we get a line search technique which does not even need any method like bisection or golden section search or Newton's method, second method, nothing, no method, just check by Armitage's rule only. And the rule of that is an alpha is considered acceptable if alpha itself satisfies the rule, but eta times alpha fails it. Okay, where eta is greater than 1. Now, what eta to take? You can take 5 to 1.5, etc., depending upon what expanse you expect to cover or what expanse is needed to be covered. Okay. So the way to operate it is very simple. Start with some arbitrary alpha, test Armitage's rule. If it passes, test it at eta times alpha, and continue. And go on testing till it fails. When it fails, then you say that, well, now this one has passed. That is the last, all these fellows were passing, and then the next one is failing. So that means the last one that passes, that's enough decrease, and after this, nothing more is expected. Now you are tracking actually. Okay, now we are tracking. If the first arbitrary alpha, first arbitrary alpha, if Armitage's rule fails, then you reduce alpha with the same factor eta and go on testing, and the first one that passes, accept that. Okay, actually, if you had, you will get the same thing from both sides. So initially you did not know what would be fine, so you could start from very low or you could start from very high. If you started from very low, then this is how it will proceed. If you start from very high, then this is how it will proceed. So the last alpha which satisfies, after which a higher alpha with eta factor would not satisfy, that is the alpha that to take. And this is Armitage's rule tracking, and it works. See, this same function, same starting point, same direction. Okay. I'll show you two runs. Started with, okay, so here I've taken eta is 1.5. So started with half. Okay. Evaluated, tested Armitage's rule, passed. So 1.5 times 0.75. Again evaluated, checked with Armitage's rule, passed. 1.125, pass. 1.6875, pass. 2.53, fail. So it is negative. So the moment it fails, we take the last one. Okay. So 1.6875 is accepted. If we had started very high at 5, okay, to begin with it would fail. Okay. Then reduce it by 1.5 factor, 3.33, again failed. Again reduce 2.22, again failed. Again reduce 1.48, pass. And take this. Okay. So either you have started with a very high value and come down, 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 down. The moment it passes, you take it. Or you start from very low. I mean, you don't know that it is very low. You start from somewhere, it turns out to be very low. You go on high, 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 high. Keeps on passing, 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 passing. The moment the next one fails, just come back and say, no, this is fine. Okay. So this is Armstrong's rule with tracking. So you increase it one way or decrease it one way monotonically. So this is actually a very good policy and it works nicely. You don't need any derivative. Okay. So, and you did not need any single variable method either. But that doesn't mean that single variable methods are of no use. This can operate only for inexact line search. Okay, it does not replace univariate optimization methods. But we have some ways to conduct efficient line searches. Okay. Now, let us summarize the important points to note. In the line search subproblem of a multivariate problem, often it is efficient, it's better to leave the line search process a little before you get hold of the optimal point. That will increase your efficiency. Because from there, you will again do something more. That's not the final point. And two notions are sufficient reduction in function value and less chances further for improvement. These are called Armstrong's rule and curvature condition. Together, they are the Wolff's conditions. With tracking, either forward or backward, Armstrong's rule alone also can be made to give very good results, which are useful in inexact line search. Okay. With this, single variable optimization in all its ramifications is over. And in the next lecture, we will start with multivariate optimization. To begin with, unconstrained optimization. Thank you.